Now, it takes many billions of years to create a galaxy, like the Milky Way galaxy, with 100 billion stars, many billions of years old.
When the James Webb Space Telescope, JWST, opened its golden honeycomb eye to the depths of the cosmos, the world held its breath. Scientists had waited decades for this moment, a chance to see deeper into the universe than ever before, but no one expected what it would uncover just a few months into its mission. Amid the mesmerizing images of stars and galaxies that dazzled the public, a particular discovery slipped through with little initial fanfare. A set of galaxies so ancient, so massive, and so luminous that they should not, by any known model, exist. These galaxies didn't just challenge existing astrophysics, they defied the very scaffolding upon which modern cosmology is built. Before we start, hit the like and subscribe buttons for more updates. Spotted at redshifts, suggesting their light originated just 300 to 500 million years after the Big Bang, these galaxies exhibited characteristics that sent ripples of disbelief across the scientific community. In those earliest epochs of the universe, matter was supposed to be in the process of cooling, collapsing, and assembling the first primitive stars and small galaxies. Instead, Webb revealed objects with mature structures, rotating disks, significant mass, and elements typically found only after extensive stellar evolution. The problem wasn't simply that these galaxies existed, but that they seemed fully formed at a time when matter shouldn't have had time to assemble in such complexity. The implications were immediate and chilling. If the universe harbored such colossal, mature structures within its first few hundred million years, then either our understanding of galaxy formation is profoundly incomplete, or our model of the universe's timeline is fundamentally flawed. The lambda CDM model, which integrates dark energy, lambda, and cold dark matter, CDM, has been the bedrock of cosmology for years. This framework predicts a slow, hierarchical buildup of structure, small galaxies merging over billions of years into the massive ones we see today. But the Webb findings seem to obliterate that narrative. These galaxies weren't small, primitive puffs of stardust, they were titans. Tens or even hundreds of times more massive than what any simulation would expect from that era. What the JWST effectively did was tear open a gaping hole in the timeline of the cosmos. Standard cosmological equations can't stretch far enough to explain how so much matter could coalesce into such organized systems so soon after the cosmic microwave background radiation cooled. The notion that galaxies like these could already contain complex chemical elements, implying several generations of stars had already lived and died, pushed the limits of what stellar evolution could even mean in a young universe. It wasn't merely puzzling, it was terrifying. One possibility now being considered is that the rate of star formation in the early universe was significantly faster than previously thought. But even that stretches the limits of credibility. Star formation is governed by fundamental physics, gravitational collapse, pressure balances, radiation. The speed at which stars form isn't just a matter of theory, it's rooted in physical processes we observe locally and at scale. To accelerate those processes by an order of magnitude or more would mean changing the very constants of nature, or suggesting that the early universe had different physical laws altogether. Others began speculating that dark matter, a mysterious component of the cosmos that doesn't emit light but exerts gravitational influence, may have behaved differently in the early universe. Perhaps dark matter clumped faster, drawing in normal matter more efficiently than expected, allowing galaxies to form earlier. But again, that would mean rewriting the properties of dark matter, something scientists have spent decades trying to pin down. Such an adjustment wouldn't be a minor patch. It would be a sweeping revision of one of the pillars of physics. Then there's the suggestion, whispered at first but growing louder, that maybe the expansion rate of the universe isn't what we thought it was. If the universe is older than we estimate, those early galaxies might not be as impossible as they currently seem. But that would mean reinterpreting the cosmic microwave background, recalibrating distances and timescales, and possibly revising the Hubble constant, already a source of tension among physicists due to discrepancies between different measurements. Adjusting the universe's age to accommodate these findings would have cascading effects across every model of cosmic evolution. More radical thinkers propose an even more unsettling notion. Perhaps time itself unfolded differently in the early universe. This idea teeters at the edge of theoretical physics and verges into territory that borders on metaphysical. Could time have ticked at a different rate? Could the passage of time itself have been warped by the density and energy of the infant cosmos, creating a kind of temporal illusion that makes young galaxies appear older than they are? Such speculation, while intriguing, also risks undermining the very consistency of physical laws across time and space, something physicists have long held as sacred. The shockwaves of this discovery aren't limited to astrophysics alone. Particle physics, too, is feeling the tremors. The early formation of such complex galaxies suggests an environment rich in heavy elements like carbon, oxygen, and iron, elements forged in the hearts of stars. Their presence indicates not just star formation, but stellar death and recycling. That in turn implies supernovae, neutron stars, possibly even early black holes that merged to form the seeds of the supermassive black holes we see anchoring galaxies today. And again, all of this would have had to happen in an unimaginably compressed timeline. The JWST's instruments picked up detailed infrared signatures of these galaxies, allowing scientists to estimate not only their distance, but also their composition and morphology. Some of them showed signs of rotational motion, a hallmark of galactic disks. And that too is deeply problematic. Galactic disks are fragile structures. They're easily disrupted by mergers and turbulence. For such order to exist in such chaos contradicts the idea that the early universe was a turbulent sea of collisions and interactions. Order emerging from chaos is a beautiful idea, but in this case, it might be a physical impossibility. The fear among many in the scientific community isn't just that the JWST discovered something anomalous. Anomalies can usually be folded into existing theories with some tweaking. No, the fear is that what the telescope uncovered points to a systemic error in our understanding, one that can't be patched, one that demands a fundamental re-evaluation of how the universe works. It's not just that galaxies formed early, it's that they broke every rule in the cosmic playbook when they did. These findings also reopen philosophical questions about the universe's beginnings. Cosmology has long wrestled with questions of origin and structure, but there was a sense, at least until now, that the major outlines were in place. The Big Bang happened. The universe cooled. Gravity gathered matter into clumps, and over billions of years those clumps became galaxies, stars, planets, and life. It was a beautiful, elegant story. But the Webb observations suggest that story might be missing entire chapters, or worse, that it was written in the wrong order. And there's the growing unease about how many more such surprises JWST might reveal. If this is what we saw after only a few months of observation, what lies ahead in the years to come? What else might be lurking in the dark, forgotten corners of the early universe? Structures, phenomena, or laws we never imagined. The telescope was built to be a time machine, and it's doing its job with ruthless precision. But instead of confirming what we expected, it's showing us a past that never should have existed. Many scientists are now returning to the drawing board. Simulations are being revised, papers rewritten, conferences held, and hastily organized emergency sessions. But even with computational brute force and theoretical flexibility, reconciling the existence of these early galaxies with known physics remains elusive. It's as if the cosmos itself is mocking our arrogance, daring us to understand it, only to slip further away with every new discovery. Yet amid the discomfort and disbelief, there's also a strange sense of awe. What the James Webb Space Telescope has done is open a new chapter not just in astronomy, but in the history of human thought. By breaking our models, it has forced us to imagine new ones. It has reminded scientists, and all of us, that the universe is not obligated to conform to our expectations. It simply is. And our task is not to make it fit our stories, but to listen carefully, and perhaps rewrite the stories altogether. In the months following this discovery, debates raged over the precise measurements. How solid were the redshifts? Could there have been observational error? Might the masses of the galaxies be overestimated? Every avenue was explored, but the data continued to hold. The galaxies were real, their light was ancient, their mass, morphology, and composition were consistent across independent analyses. And most damningly, they were not alone. More such galaxies began to emerge in the JWST's field of view, forming a population too large to dismiss, too structured to ignore, and too old to explain. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on this discovery? Will it rewrite physics as we know it? We want to hear from you. Thank you for watching, and see you next time.